The Chromium Deception, How the World's Mineral Reserve Data Became a Managed Lie. Why chromium matters. Chromium has no substitute in stainless steel, the leading end use, or in superalloys, the major strategic end use. That's not an opinion. That's the USGS's own assessment, printed in every annual commodity summary. Surgical instruments, jet engine turbine blades, chemical plants, nuclear reactor containment vessels, stainless steel in all its forms. Chromium is embedded so deeply in industrial infrastructure that removing it is not an engineering problem, it is an impossibility. Without chromium, there is no industrial civilization as we know it. A note on language. Before we get into the data, a note on the language I'll be using. The metric prefix milli means 1,000th. The word million sounds like it belongs to the same system, but it means something 6 orders of magnitude in the opposite direction. The prefix bi means 2, but billion means 1,000 mega. These words are etymological nonsense that became convention. Consider why we say millionaire and billionaire instead of megallionaire and gigallionaire. The familiar words psychologically deflate the scale. A person earning minimum wage would need to work roughly 30,000 years to earn what a gigallionaire holds. The word billionaire hides that. Gigallionaire does not. The same psychology applies to resource numbers. Comfortable words prevent people from feeling the weight of what is actually being described. Throughout this presentation, I'll use megatons, not million tons. Gigatons, not billion tons. Same numbers. Honest prefixes. The limits to growth. In 1972, the Club of Rome published The Limits to Growth, a landmark report examining 5 factors that limit growth on a finite planet: population, food production, industrial production, pollution, and non-renewable resource depletion. On page 56, Table 4 lists chromium reserves. The report states, known global reserves 775 million metric tons, of which 1.85 million metric tons were mined annually. This sentence contains a critical error that has never been corrected. The error. The report uses the word chromium interchangeably with chromite ore. These are not the same thing. The truthful sentence would read, in 1972, the amount of shipping-grade chromite ore reserves was 775 megatons, from which approximately 6 megatons of ore were mined, from which 1.85 megatons of chromium metal were produced. The distinction matters enormously, and the failure to make it has been perpetuated, knowingly or unknowingly, in every major resource publication since. The conversion chain. From rock in the ground to usable chromium metal, there are multiple conversion steps. Raw ore is mined and beneficiated into shipping-grade chromite ore, which is normalized to 45% chromium oxide. Chromite itself contains 68% chromium metal by weight. After all conversions, the actual chromium metal content is roughly 30.6% of the headline or figure. When public reports say 775 million tons of chromium, they mean ore, not metal. This distinction is systematically obscured. Extraction growth. This chart shows every single year of world chromite ore production from 1950 to 2024. Converted from the USGS data series 140. The data is reported in chromium content. I've converted it back to shipping-grade chromite ore at the standard 0.3078 factor. In 1950, the world extracted roughly 2 megatons of chromite ore. By 1972, when the limits to growth was published, that had tripled to about 6 megatons. By 2024, it reached 47 megatons. That's a 7-fold increase since the limits to growth. A 20-fold increase since 1950. And the acceleration is visible. Look at how the curve bends upward after 2000. Production nearly tripled in the last 24 years after taking 50 years to reach the 2000 level. You can also see the dips. The Soviet collapse in 1992, the 2001 recession, the 2009 financial crisis, COVID in 2020. Each time, production recovered and resumed climbing. Demand for chromium never permanently drops, it only pauses. The 12 gigaton myth. Every USGS mineral commodity summary since the 1990s contains this sentence, word for word. World resources are greater than 12 billion tons of shipping-grade chromite, sufficient to meet conceivable demand for centuries. This sentence has been copy-pasted for 30 years. Where did the 12 gigaton figure come from? A 1984 international assessment estimated 7 gigatons. A USGS specialist named John F. Papp later upgraded it to 12 gigatons by including substandard deposits that the original assessment had deliberately excluded. Stratiform versus podiform. This is the critical distinction that the headline numbers conceal. Chromite deposits come in two types. Stratiform deposits account for 96.5% of the claimed resource. These are deep underground, low-grade, and extremely expensive to mine. Even the Soviet Union, which operated mines without regard to profit, largely left these in the ground. Podiform deposits account for just 3.5%. These are near-surface, high-grade, and economically viable. This is what the world actually mines. And this is what's running out. The correction. When you apply both corrections simultaneously, the unit conflation and the deposit classification, the picture transforms. Start with the 12 gigaton headline resource figure. Take the 3.5% that is podiform and economically viable. That gives you approximately 420 megatons of mineable ore. Extract the chromium metal content at 30.6%. And you arrive at roughly 128 megatons of accessible chromium metal. At 2024 extraction rates of approximately 14 megatons of chromium metal per year, the economically viable supply is measured in years. Not centuries, years. The accessible chromium metal is roughly 1% of the headline resource figure. The doubling. In the 2025 edition of the USGS Mineral Commodity Summaries, global chromite reserves jumped from 560 megatons to 1.2 gigatons, a 114% increase in a single year. No new deposits were discovered, no new mining technology emerged, the rocks did not change. Someone changed a classification boundary. The paper trail. In the 2025 edition of the USGS Mineral Commodity Summaries, reserves jumped from 560 megatons to 1.2 gigatons. A single footnote explains, reserves for Kazakhstan were revised based on a government report. The 2026 edition changed methodology for the first time, adding a Cr₂O₃ content column alongside ore weight. It also introduced footnote 14, which describes Kazakhstan's reserve data as likely based on the Soviet-era GKZ classification system. The word likely. The agency publishing the number the entire world relies on is not certain what classification methodology underlies it. Footnote 14 also reveals that Kazakhstan's source did not even provide data for the highest confidence category of reserves. The A reserve data was simply not included, and the low-confidence C2 category had to be excluded from the published figure. The GKZ classification problem. Kazakhstan inherited the Soviet GKZ mineral classification system. It was supposed to transition to international standards by January 2024. That deadline was extended to 2026. Then the Soviet-era system was restored to run in parallel with the new one. The GKZ system classifies reserves from A, which is well established, down through B, C1, and C2, which is essentially geological inference with minimal drilling. A World Bank diagnostic from 2023 confirmed that Kazakhstan has done almost no new greenfield exploration in 30 years. The underlying geological data predates the collapse of the Soviet Union. 2 mining areas. The world's chromium supply depends on 2 geological complexes. Kazakhstan's Donskoy Gok, operating since 1938, controlled by a Luxembourg-registered company called ERG, owned 40% by the Kazakh government and 60% by oligarchs. New mines are now operating at 800 to 1,200 meters depth, among the deepest in the world for ferrous metals. ERG invested $1.8 billion specifically to replace diminishing output from existing mines. The country sits under a Russian military umbrella. South Africa's Bushveld complex holds roughly 70% of world reserves and produces 75% of the world's ferrochrome, but the deposits are overwhelmingly stratiform. Primary chromite layers are going deeper and becoming more expensive to mine. Ferrochrome smelting is one of the most electricity-intensive industrial processes on Earth, and South Africa's state-owned power utility, Eskom, suffered rolling blackouts from 2007 through 2024. Its coal power stations are 50 years old. Eskom is effectively bankrupt. That is the global supply chain behind every stainless steel product on Earth. 2 spots on the map. No substitutes. Not just chromium. The same pattern of reserve inflation, unit conflation, and classification manipulation applies across approximately 30 critical minerals. Chromium is the case study because the data trail is traceable to named individuals. But the structure is identical for copper, cobalt, manganese, tungsten, vanadium, zinc, tin, nickel, antimony, and others. Each mineral has its own version of the stratiform-podiform distinction. Headline reserves dominated by deposits that are technically present in the ground but economically marginal or effectively unminable. The timeline. Chris Clugston, building on Walter Youngquist's foundational work in Geodestinies, documented the decade-by-decade progression of resource-driven civilizational decline. The 2020s, us versus them. Our goal of universal human prosperity is attainable. There is enough for everybody. Our problem is a broken system. The 2030s, us or them. The system cannot be fixed because of them. There is enough for us, but not enough for them, so they must go. Literally. The 2040s, me or you. My problem is you, a resource competitor. As societal institutions, governance, and real wealth creation cease to exist, the survival of each individual depends on the elimination of all competitors. Who knows? The USGS tracks over 90 minerals across 180 countries. Each mineral chapter is written independently. Nobody's job description includes synthesizing across all commodities to ask what the aggregate picture looks like. At the civilian institutional level, the system is not designed to produce this synthesis. But at the highest levels of the military-industrial complex, the picture is almost certainly understood. Defense agencies publish strategic mineral assessments. The U.S. National Security Strategy explicitly names critical mineral access as a national security priority. Military bases correlate with mineral-rich regions across Africa and Central Asia. Preclusive purchasing of strategic materials has been documented U.S. policy since World War II. The public does not know. The institutional bureaucracy may not know. But the people who plan force projection and supply chain security for the next 30 years, they know. The question is not whether anyone understands the crisis. The question is whether the response will include the general population or exclude it. The question. If the corrected numbers are right, if the economically accessible reserves of chromium and 30 other critical minerals are measured in years rather than centuries, what does the timeline actually look like? Nobody in a position of authority can answer this question publicly because there is no politically survivable answer. The data is public. The USGS publications are free. The arithmetic is elementary. The only thing missing is someone willing to do the math.